So du is going to be 2e to the 2 theta d theta. V is going to be sine, 1/3 sine 3 theta.
Oh, yes, those are practice.
So what do we have here? We have the integral of e to the 2 theta sine 3 theta d theta equals 1/3 e to the 2 theta cosine 3 theta plus 2/3 times uv. Let's write it this way. And then we have v du Does that look okay, Jacob?
So you took the derivative of u, or like e to the 2 theta.
Uh-huh.
How did you get that as your result?
So it's a chain rule, right? Derivative of the outside is e to the 2 theta, derivative of the inside is 2, so I have 2 times e to the 2 theta.
Oh, okay.
Right? Does that feel okay? So now I just have some cleanup to do here. Yeah, what's up? Sorry, go ahead.
Kind of go back and label where each piece came from.
Sure. All right, let's see. Let's do some color coding. So this is just the starting problem. This is my guy out front. This is that plus 2/3, right? This is my u times v. And then this is my integral of, v times du. Is that?
No, big yes.
Yeah, no problem. Again, like, I put a bunch of stuff together there and like had some gaps and it just. All right, so I'm gonna do a little bit of cleanup here on my right-hand side. So if I distribute the 2/3 through, I have plus 2/9 e to the 2 theta sine 3 theta. And then I have minus 4/9 integral e to the 2 theta sine 3 theta d theta. And we'll just add that over to the other side. So that's going to give me 13/9 e to the 2 theta sine 3 theta d theta equals 1/3 e to the 2 theta cosine 3 theta plus 2/9 e to the 2 theta sine 3 theta. And then if I multiply both sides by 9/13, I have a solution. I just have to slap a plus c on it at the end. Elaine, does that feel okay there?
Yeah, so why is it added 4/9?
Because there's a 1 in front, right?
Oh, yeah.
And we just put a plus c at the end, and that should be my final answer, I think. Guess I should check it, right? Somebody have the book answer already looked up on that one to check it? I hope it's right. I always feel bad when I do one of these and it's like, look at this stupid thing I did. You know? Yes, that's good. The book has like a factored answer or whatever, but like good enough. Yeah. So the book has it like they did some factoring and they pulled out like a 1/13 and an e to the 2 theta and stuff, but like whatever, it's the same thing that we have here. Elena, that was a doozy there, right?
Yes,
You okay?
yes.
All right.
I seem to know where things came from, like that's where I got lost.
Yeah, there's a lot to keep track of, right? This is one where like neatness and organization really kind of help you out because it is a kind of a long trip.
I kind of lost a piece of it.
Yeah. Well, it makes it hard when you're doing like the by parts because you want to write down like your U's and V's and stuff in between. And then you have like, and I have to recopy everything back in rather than just like, just equals and then move down, because it's just like, it's a lot to kind of keep track of. Others from homework. Shoot, Rita.
Number 13, please.
Same section of homework?
Yeah.
Okay. So that's integral t secant squared 2t dt. Did I copy that correctly? Okay. Critical to do that check before we start. So our u and our dv, what do you think? That would be my first instinct as well. Yeah. So du, well, that's just dt. That's real easy. And then to integrate this, we have to do another u sub, right? So we get 1/2 tangent 2t. Right, the integral of secant squared is tangent. But you had to do like a u sub. That's where the 1/2 came in.
Sorry, will you write out the u sub?
Sure. So I said that u is equal to 2t. So du dt is 2. So I know that du over 2 is dt. So that's where the 1/2 is coming from the du over 2. And again, if you can't see that in your head, that's pretty normal at this stage of the game, right? To like do a u sub in your head quickly, even if it's just like a coefficient u sub. Not an expectation that you're able to do. In the interest of time, I'll do it on occasion, announcing that I'm doing it. But if you can't see it, you're fine. That's normal. You've done, a few dozen u sub problems in your life. You should, be like instantly confident to do stuff like that in your head because it's not trivial. Okay. So what do we have here? We have our starting problem equals u times v minus the integral of v du Does that feel okay to hear?
Yeah, I got this.
Okay. Want to remember in our notes. What's up?
I just need to talk to Giselle.
Oh, yeah, go ahead. That's what we did. I was like, did we do the integral of tangent already? Okay, we did it. All right. So you're struggling at the integral of tangent 2t, right? Okay. So here's what I'm going to do. I'm going to do this as a u sub problem. But to do it as a u sub problem, I'm going to think about tangent 2t as sine 2t over cosine 2t. So when I do that, my u is going to be cosine 2t, and my du dt then is going to be negative 2 sine 2t. So I have du over negative 2 is equal to sine 2t dt. So let's recopy and put some stuff in so you guys can see what happened there. So I'm going to have 1 over u, right, because that's cosine from the denominator, times du over negative 2. That's the sine 2t dt. Everybody's okay there? So I have t over 2 tan 2t minus, well, really plus now 1/4 natural log absolute value u plus c. And then I just have to plug my u back in, which was sine or cosine 2t. I think that's probably what the back of the book has. Huh. Let's take a look. That felt pretty good when I was doing it. Let's take a look. This is 13. Oh, it's the same thing because they have minus natural log secant. So if you push that negative exponent in, because there's a negative sign out front, that's like a negative 1 out front. So you could use your logarithm rule to make that a negative 1 exponent inside the logarithm. Cosine to the negative 1 is, or secant to the negative 1 is cosine. So this is equivalent to what they have. So I'm going to, I don't know, I didn't look to see exactly what they did, but our answers are equivalent. So I'm going to just, this felt good. Let's just stick with this. Okay. All right, my peeps. You ready to go? Welcome to the land of differential equations. Here's the good news. This is no harder than anything we've done. Conceptually, it's pretty straightforward. It's all application, so there's not a lot of like theoretical conceptual pieces. There's not like any theorem to speak of. So it's all like application, symbol pushy, kind of should feel comfortable inside of our, what you've told me is your wheelhouse, right? Okay. So when we talk about a differential equation, that simply just means it's an equation with a derivative value in it. So it has like a y prime, or it has a dx dy, or dy dx in it, or something like that. One of the first kind of applications that we like to talk about when we talk about a differential equation is usually like a population situation. So that's kind of where we're starting here. So for a population growth, we have kind of two variables. You have time and population. So we're going to use T for time and P for population. So what we do is we start with a differential equation. So we say that we're going to start with the assumption that population grows at a rate that's proportional to the population. So if you have more people, the population should be growing faster than if you have just a couple of people, which seems probably right intuitively. So we'd say then dp dt, the rate in which the population grows, is equal to k, some constant, that's what proportional means, times p. So when you see the word proportional, you're talking about k times something. Note here that we assume anyways, keep on going. So if k is we assume the population is non-zero and non-negative, right? Because it's a population. If you have zero things to start with, you can't reproduce, and you certainly can't have negative populations, right? Like that's all a normal assumption. So if k is positive, then our dp dt also has to be positive because you'd have a positive times a positive, right? K is positive, p is positive, so the population growth should be positive. Everybody's good with how we got to there? That would imply the population is always increasing. And furthermore, it would say that as p of t increases, the derivative of p should also increase. Everybody agree with that? Okay. So the question is here, what we're looking for is a function whose derivative is a constant multiple of itself. Yeah, e to the x. Excellent. Now, we'll probably write it this way, like e to the kx. So the derivative then would be like k times e to the kx. Again, when we say constant multiple of itself, k is that constant multiple, right? I mean, e to the x is fine because 1 is a multiple, but like we want to use something a little bit more abstract there because we didn't designate that is in fact itself. It could just be any, 2 times itself or 5 times itself or a half times itself, whatever. So if we consider all possible solutions to this differential equation, it was just some exponential equation, right? And it could be shifted up or down because you'd have like a plus, you could have a plus c on at the end that just gets destroyed when you take the derivative. So we have like infinitely many solutions, right? Now, again, we said that population can only have positive values, so we can discard all that stuff down there because negative population, we said that wasn't going to be a thing we could consider. So we have something like this. So now let's think about in real life. Is a population going to continue to grow always? No, right? When would that work? When would the population behave this way that we're seeing, where it's just growing at a constant rate? Yeah, good. So like when resources are plentiful, right? Kind of in under ideal circumstances. So you have like enough food and you have a lack of competition or predators and like all that kind of stuff. Now as population grows, what's going to happen to those things?
Run out.
Right, like predators increase because if you have more things to prey on, there you're going to have more predators. As your population grows, you're going to have depleted resources. So really what ends up happening is you get something that behaves asymptotically, like you get to like a carrying capacity and then you just don't, your population can't grow anymore because you're just at the capacity of your environment, right? Like there's no more resource to use. You've taken up all the space there is available. Eventually you kind of reach a carrying capacity and it's like, it's kind of as much as we can do. Can't get any more because there's just not enough resources to support it or there's too much competition or whatever it is, right? So a model that describes this pretty accurately would be a logistic model. Remember what a logistic curve looks like? Kind of like that. Where in the beginning it grows exponentially and then at the end it like tapers off and kind of grows logarithmically, like there's an upper, like two asymptotes on this, right? You have like a lower asymptote and you have like an upper asymptote. Feel okay with remembering that? We talk about those last year, but it's at the end of the semester and you're sometimes attention spans go, right? So ideally what we'd want is a model that behaves exponentially when that population is small, where resources would be plentiful, and then becomes negative. The growth rate becomes negative if your population ever exceeds that carrying capacity. So like, for example, if you like dip over here, it would want it to come back negative. So you end up back at the carrying capacity, right? So to do that, what we're going to say is, okay, we can change our differential equation by adding on this extra factor of 1 minus P over M. So remember, P is the population and M is our carrying capacity, like the maximum population the resources will allow us to maintain. So what happens if P is less than M? Well, the fraction P over M would be less than 1, right? So 1 minus that number is a positive, so that your population growth should still be positive. If P becomes greater than M, P over M is now greater than 1. 1 minus P over M is a negative number. That's now going to make your growth rate negative, which is what we want it to do. If you get up above the carrying capacity, population needs to start decreasing because you're out of resources or out of space or whatever. Is that now everybody feel good about how that's describing exactly what we want it to do, right? Okay. All right. We talked about what happens here. So here is what our solutions might look like. Notice that we talked about how logistic curve has those two asymptotes. Those would be equilibrium solutions, right? If the population becomes 0, well, this thing is just stuck at 0, right? If the population becomes M, this is then stuck at 0, right? Because M over M is 1, 1 minus 1 is 0, whole thing zeroes out. Does that feel okay? Being able to find the equilibrium solutions to a differential equation is going to be a skill that we're going to want to develop. So being able to look at the equation and figuring out what the equilibrium solution should be, or in the reverse, we'll look at something called a slope field. We'll talk about what that is in a minute. And figure out what the equilibrium solutions would be so we could pick out the correct differential equation to match a slope field. A slope field kind of resembles something like this, but it's not as, there's no lines. We'll show you in a minute. It's a fairly easy thing to wrap your head around if you look at it for a minute. I'm being serious. Like, it's very much you just need to use your eyes. There's no calculation. It's going to be really involved. Okay. So that's an example of using a differential equation to model a real life situation. Is anyone going to ask you to create a differential equation model on the AP exam? No. Is Mr. Kulik going to ask you to do this? No. So let's look at what we might ask you to do, right? So we've seen that, like, as an application, anything in the real world that's changing, you might want to model by writing some kind of differential equation, right? But let's look at just kind of generally when we talk about a differential equation, what we mean. So we say a differential equation is an equation that contains an unknown function and or one or more of its derivatives. For example, y prime equals x times y. Everybody's cool? Differential equation, because it has a y prime in it and a y, and it has an x also. The order, when we talk about the order of a differential equation, we'd say this is a first order differential equation because the largest derivative it contains is a first derivative. If I had a y prime or y double prime equals xy, that would be a second order differential equation because it contains a second derivative. Everybody feel good? Probably in this class you won't see anything bigger than a second order differential equation. And that would be sparingly that you could see that. We'd say a function f is called a solution to the differential equation if the equation is satisfied when y equals f of x and its derivatives are substituted into the differential equation. So if I took my solution, y equals f of x, and I take the derivative of that, that would need to equal x times f of x. So that's all I'm going to do to check it. I'm just going to plug the functions back in and make sure the two sides are equal. If they are equal, then we'd consider it a solution. We'll show you guys in practice here in a minute doing that. It's not terribly complicated. Can be a hassle algebraically, but it's not terribly complicated to do. The idea is not terribly complicated. To solve a differential equations, we're expected to find all possible solutions of the equation. And this is something we've done already. How do we do this? We just put a c at the end, right? Plus c. And then, it's all possible, right? If we had the derivative of y is equal to x cubed, and I do the integral, like of both sides, I get x to the fourth plus c, or x to the fourth over 4 plus c, right? No big deal. All right. Let's look at a example that's a little bit complicated to kind of reinforce this idea of showing that something is a solution. So it says, show that every member of the family of functions, y equals yada, 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 is a solution to y prime equals 1/2 y squared minus 1. So this is my y, right? So the first thing I'm going to do is calculate y prime. What do I need to do to calculate y prime? How do I do the derivative of this? I use the quotient rule. How do I do the quotient rule? So it's the bottom times the derivative of the top. What's the derivative of the top? C times e to the t, and then it's minus the top times the derivative of the bottom. What's the derivative of the bottom? Negative c e to the t, all over great, the denominator squared. Excellent. So far, so good? Let's clean this up a little bit. So I'm going to get c e to the t minus c squared e to the 2t, and then minus the negative is going to make that just a plus c e to the t plus c squared e to the 2t. Everybody's okay? Did you notice anything good happening there? Yeah, we have some stuff that cancels, right? So this just becomes 2c e to the t over 1 minus c e to the t squared. Okay, so that's going to be my right-hand side here. Oops. So y squared is going to be my y, and then I have minus 1, right? Does everybody feel okay with what I've written so far? Ugh, come on now. You stupid machine. Why is it doing this? I don't know what's going on here. Can we give me some more space here, you stupid machine? I don't want to make any text boxes. All right. Still doing okay. So on the right-hand side, when I have the exponent of a fraction, I can apply that exponent to the numerator and denominator, right? And then to subtract that 1, I need to make a common denominator. So I have that, right? What's going on? Why is this being so weird? Usually I can just start pressing enter here and it just toggles everything down. Super annoying. Okay. Now I'm going to FOIL out the things in my numerator. So I'm going to FOIL that out and FOIL that out. Notice that I'm distributing the negative sign along the way, right? Because I have this negative right here. So I distributed that while I did that, or while I foiled. Is that okay with everybody? Then I'm just kind of giving a little bit of narrative here instead of like grinding through every little grimy detail. Okay, what do you notice here? Yeah, so that goes. And if I multiply the 1/2 through, that would cancel those 2's, right? So what I'm left with is c e to the t plus c e to the t. That's 2c e to the t's over 1 minus c e to the t squared. And that is what we needed, right? This is a particularly tedious example of verifying this, but the calculus idea, we did one derivative here, and everything else was just like grinding through some tedious algebra, right? Very simple calculus idea, right? We're just taking the derivatives and plugging them in, plugging the equation for y in for the y's, and then just making sure the two sides are equal, right? So it's mostly just tedious algebra. Let's do another example. Okay, here it says to find a solution for the differential equation that satisfies the initial condition that y of 0 is equal to 2. When you see an initial condition like this, we know that all that's going to be used for is just to find the value for c. So whenever you're given an initial condition with a differential equation, that's just to figure out what c is. Okay. So we have y prime equals 1/2 y squared minus 1. We'll do the integral of both sides. What's the integral of y prime? Y. And then the integral of 1/2, I'm sorry, 1/2 y squared minus 1. Oh my goodness, guys.
Oh, wait.
Hold on a second. I'm so dumb. Hold on. I'm not dumb, but I'm like pretty dumb. This is still referencing this y. We don't need to find y. We already have it. My apologies. Yikes-a-rooskies. So what we're trying to do with this y is just solve for the c. So we know that y of 0 is 2. So we have that, right? I've just taken my equation for y. What's e to the 0? 1. So those just kind of like disappear, right? So to solve for c, I'm just going to multiply both sides by 1 minus c. I subtract 1 from both sides and add 2c to both sides. and I get that C is 1/3. Everybody's okay with that? You think that's how the multiple choice answer to this would look?
No,
I doubt it. What don't you like about this?
it's not fully simplified.
The fractions inside of the fraction, right? What would we do to get rid of the 1/3? Yeah, multiply the top and bottom by 3. That answer would probably be a multiple choice answer as opposed to the other one, but if it's a free response question, you don't have to worry about it. You know what I mean? All right. Does everybody feel okay about this, like how to show something as a solution? And then use the initial condition to find the C?
Will they normally give us a Y?
Yeah, so like the questions in the homework look like this.
Oh,
We haven't shown yet how to find that solution to a differential equation yet. But this is a skill that I've seen like asked for directly on, like an AP thing. Or give you a multiple choice, like here's the differential equation, which one of these is a solution to it? Usually they're not algebraically as complicated as that one that we did as in the example, because that's just like a kind of a pain in the tuchus. There's a lot of algebra. Okay. Section 9.2 is about what our textbook calls direction fields, but I think the AP always calls a slope field. So what a slope field looks like is something like this. What these blue lines represent is the slope of a differential equation at some point. So like if this is the point like 1, 1 here, it's saying like the slope for my differential equation would be, or the slope for my solution to my differential equation would be like that. So you're seeing just like a bunch of possible solutions to a differential equation. Let's kind of see that. All right, let's go back and to the beginning here. And so let's say we wanted to sketch the graph for this differential equation, y prime equals x plus y, with the initial condition y of 0 is equal to 1. So what this differential equation is saying is that the slope for our solution should just be the sum of the coordinates at that point, right? So if we're at the point 2, -1, then the slope for our solution should be 1. So like 2, -1, if I plotted that point, I should draw a line with a slope of 1. Just a little segment, right? And I could do this for all the points I wanted to, right? If I do that for all the points I want to, I get something called a slope field. That's what we're doing here. That's what we've drawn here. Would you be asked to construct your own slope field? Possibly, but it would just be like, here's 9 lattice points. They would give you like a finite number of points to just like construct a slope field for this, where it's like, okay, I just have to do like 9 little calculations and I can draw this. I would not ask you to do it, probably on a test or whatever, just because it's time consuming and I'd rather have you spend your time doing something else. But I've seen practice AP questions where they ask you to do this. It's not difficult, but it can be time consuming. So what if we wanted to use that? So here's our slope field, right? We've constructed this just from the differential equation. And we have this initial condition, y of 0 is equal to 1. So when x is 0, y is 1. So that's like that point there, say maybe. Well, actually, it's probably more like that point there. Everybody's okay there? And I can see from the slope field that like the slope at that point should be that, right? Which is what I've drawn here. And if I transfer that on top of the slope field, I can use the slope field to kind of sketch a possible solution just by following the slopes in the slope field so that they pass through that point 0, 1. Right? So if I go back and I look at this thing, it's okay. Oops, so Daisy, what did I just do? I think I somehow copied and pasted something I didn't mean to. So it's like, should kind of go like that, right? That's just me kind of making a sketch. When I actually did it, looks pretty darn close. Would this be something I ask you to do? For sure. Would this be something AP asks you to do? For sure. Is it difficult to do? Not really, right? Like, pretty straightforward thing to do. Okay. So let's say you're asked to sketch a direction field or slope field for this differential equation, y prime equals x squared plus y squared minus 1, and then to sketch a solution that passes through the origin. So this is just me doing some work on how I would sketch my slope field, right? So I just picking different x's and y's, plugging them in to get the slopes, and then transferring that onto this picture. Okay, I did all of that for you because it's a hassle, just time consuming, right? Okay. So origin is there, right? So if I draw my slope field, it's going to kind of do one of those and kind of do one of those. You guys buy that? Okay. Feel good on doing this? It's not really any calculation to speak of. You just have to like know what it is you're looking at, right? Not too bad. All right. Where's the rest of my stuff? That feels like there's something there that just I deleted somehow. Maybe not. All right. So this differential equation, y prime equals x squared plus y squared plus or minus 1, we call an autonomous differential equation because the right side did not have the independent variable t. No, that is not at all what this is referencing. Okay, I'm missing an example here. Yeah, I thought something looked like it got deleted on myself. All right, let me just, that's better. So let's say that we know that Ohm's law gives us a differential equation like this, where so we're told here that, what is this? Inductance is L, so that's a 4. Resistance is R, so that's 12. And then E, energy, is like our voltage. So I could like divide both sides by 4 to just like simplify this guy down a little bit. And then just get the di dt by itself. And now, if I draw my direction field for this, let's just pretend through the magic of Mr. Kulik that we've done this. Again, I wouldn't ask you, I thought I was pretty careful on the homework as to not ask you to do this a bunch of times. Oh my gosh, Mr. Kulik, you're just making a huge mess here. I'm just gonna, what's up?
Did you miss me?
Yes, you're back. What's up?
I need to talk to Gigi for a second.
Okay.
I could use yellow across the middle. You want on your senior graduation, like yard sign? Do you want us to say, we do yard signs for graduates? Congratulations, class of 2024. Do you want yours to say Gabriella or Gigi? Are your parents gonna be okay with that? That's all
I think they should just put the 2 letters. What do you think? All right. So let's say that we got this differential or this slope field for that differential equation. What appears to be the limiting value here, or the equilibrium value here? 5, right? And that's an I value, right? Why would that be a limiting value? Yes, but look at what happens over here. What happens when I is 5? The slope is 0, right? Everybody's okay? So again, you can find these like equilibrium values just by figuring out where the differential equation is equal to 0. That should be reflected on a slope field where you should see the horizontal pieces on a slope field, right? The flat slopes. Okay. That's fine. I don't want to do any of these other parts. So that type of differential equation we just looked at, we call an autonomous differential equation because there is no t, right, in the right-hand side. This is di dt, but there's no t's over here. So any slopes corresponding to two different points with the same y-coordinate have to have the same slope, right? Like if you look as we move like across, all of those points have different x's but the same y, and they all have the same slopes because, well, the slope doesn't depend on x at all. It just depends on y, right? So again, that's something that you can observe looking at a slope field and say, oh, look, as I go from right to left, all the slopes are the same. This can't have any x values in your differential equation. Or if you go up to down and all the slopes are the same, well, there can't be any y value in your differential equation, right? Does that make sense? Again, very common AP question would be like, pick the differential equation that matches this slope field, or which slope field matches this differential equation. So I'm just trying to build some intuition as to like how to do that effectively. You know what? We're not going to do Euler's method here because that's a BC question. I just don't want to worry about it. So we're just going to skip this. Everybody okay there? All right. So let's take a look here. These are some of the homework problems. Let's do a couple. So I'm interested in like 1B. Look at that slope field there. What are the equilibrium values? So you have to indicate the variable. Just y equals 1.5 is fine. Okay, do you see any others? You should. Okay. So what would the differential equation possibly look like for here? So it could look like something like that, right? Because if x is 0, slope is 0. If y is 1.5, slope is 0. If y is 0.5, slope would be 0. Does everybody kind of see that? Do I know that that's exactly going to be what it is? No, but I know the equilibrium values say that part of it, like there could be some other stuff going on in there, but I know the equilibrium values are telling me that part has to be true. You know what I'm saying? Well, y is 1.5, right? So why would that make... Yeah, 1.5 minus 1.5 is 0. That's what I want, right? Is that...
Yeah.
Okay. Let's look at this one. What are equilibrium values here? I would guess here that y equals 0, looking at the pattern from before. Right? Like these slopes are getting flatter as we move down. You guys see that? So like as I go down, those slopes are flattening out. Looks like the next slope at y equals 0 would be flat. What else do you notice here though? Yeah, I have some verticals here at, right? So what is that? What would that tell me? Nope. So, like my dy dx, my numerator might be like y times y minus 2 times y minus 5 or something like that. But the denominator, when y is 1, should be 0. I should be getting vertical slopes, right? And when y is 3, I should have a denominator of 0 because I should be getting vertical slopes. So like when you see a vertical slope at a specific value for x or y, that's telling you that the denominator should be getting 0, or something is undefined, right? Most commonly, it's going to be a denominator, or 0 denominator. Does that feel okay there? You see how I kind of looked at the slope field and was able to tell stuff about what the differential equation would look like? Okay. What are you guys thinking? Is this pretty okay? Yeah? All right. Let's do this next one. So here we're supposed to be matching the slope field to the differential equation. So I would probably start with the differential equations. What would be an equilibrium values for 3 here? 2. How about this one? Y equals 2 and x equals 0, right? Okay. Let's go and look at this one up here. None, right? There'll be places where you have 0 slopes, but it won't be strictly, like one based on one variable, right? So like when x is 0 and y is 1, well, that would give you a 0 slope. But x is 1 and y is 0, that would give you 1. Or when x is 2 and y is 1, or x is 1 and y is 2, whenever they differ by 1 unit. What about here? Where is sine equal to 0? At 0, pi, 2 pi, etc. Okay. So I notice here that none of my 3 equations have the exact same equilibrium values, right? So that's what I'm going to use for my separator. So if I look here, I see this one has y equals 2 and x equals 0. So that one would have matched up with number 4. Here I see just y equals 2. So that would have matched up with number 3. Here I see no equilibrium values. So that one should match up with number 5. Where the slope is 1.
Yeah.
So if I put in or negative 1, I should say, if x and y are opposites, like 1 and negative 1, what's the slope going to be? Negative 1, right? So if I look down that's exactly what I'm seeing, right? When I have 2, negative 2, the slope is negative 1. When I have 1, negative 1, the slope is negative 1. That's exactly what I would expect from that. Does that feel okay? So process of elimination then means that this next one has to be the one for 2, which is great because I see, again, y equals 0, x equals 0, and then over here at pi, y equals pi, I should say, or I'm sorry, that's x equals pi, and then up here at y equals pi and down here y equals negative pi, right? Because if x or y is constant, I'm not going to get 0 from anything, right? Because I have that extra -1 there, and they're being added instead of multiplied, right? So like there's not a single value of x that always makes the thing 0, or a single value of y that's always going to make the thing 0, right? If I pick x and y, values of x and y, I can make it 0, but I can't make it always 0 just by controlling it with one of the variables. Does that make sense? Everybody's cool about how I went about doing this? This is a skill that you should have, okay? All right, feel good about stopping here?
Yes, like for number 7, what field is it talking about? Like what area are you able to do?
So see the Roman numerals?
Oh, like that.
So it's talking about this guy right here.
Oh, straight on it, okay.
Is that cool?
Yeah.
Okay. Again, this section 2 homework should be relatively quick, unless they ask you to sketch a direction field, and I think I avoided most of those questions because, quite frankly, it's just a really time-consuming skill that, like, maybe doing it once is fine, but, like, having to do it a bunch of times is, like, super annoying. It's like, Jesus, Mr. Kulik. At least, like, narrow this down so it's, like, in the first quadrant between, you know, x is 3 and y is 3 or something. So you only have, like, 9 points to deal with or something.